Okay. Um, all right. If there are no questions on anything else, are there any? Okay. I saw Melissa's name highlighted, and I thought she might be trying to come back in. Okay. Well, where we left off last time, I think we just finished section 4.2, and we're getting ready to start 4.3, which follows very nicely to what we were doing in 4.2, as you'll see in a minute. Well, a few minutes maybe. Now we finally start actually solving some homogeneous linear equations with constant coefficients. 4.1, 4.2 were giving us tools we needed to do this, and it seemed like they went on forever. But now we're getting close to being ready to solve some equations. So here's what we're doing. I won't read all this, but basically, if you have, now here's the key, homogeneous. Now that isn't the same homogeneous that means all the terms have the same degree of the exponents. That's of the coefficients. That's not at all what this one means. Homogeneous means it's equal to 0. Whatever your differential equation is equal to 0. Every one of these differential equations equals 0. That's what we're meaning by homogeneous now, and pretty much most of what we're going to be doing from now on. At least, well, we don't have that much time left, but for now. Okay, so homogeneous. Linear equations, remember, you can't have a y prime multiplied by a y. You can't have a y prime squared. You can't have anything such as that. They have to be, and you can't have a function of y as a coefficient. You can't have that. Okay. Let's talk about the coefficients then. Right now we're dealing only with constant coefficients. No more even x's in the coefficients. Constant coefficients. So homogeneous equals 0. Linear, you know what that means, constant coefficients. So it's a pretty simple thing. And here's basically a first order linear equation, homogeneous equation with constant coefficient. AY prime plus BY is equal to 0. Okay? Now, I'm about to yank something off the tabletop desktop here, and I'm trying not to do that. Okay. And by the way, can you hear me okay? My phone went out, or microphone went out yesterday in the second class, and it did that again last Thursday, and my wife has managed to fiddle around with it and get it working again. So if it starts giving problems, let me know. Okay. So that's what we mean. If you solve this equation here for y prime, in other words, you subtract by from both sides and then divide by a. So that would give us y prime is equal to b over a times y. Well, rather than call it b over a, they call it k. Okay. Now this is an observation here. This is not how we go about solving these, because we are now in higher order differential equations. Remember, that's what chapter 4 is all about. This is a linear, okay? But now the k is a constant, and guess what? You could solve that by separation so easily. But here's the observation they want you to make. If y prime is equal to some power some constant times y, the only function that's guaranteed always to do that is what function? When you take its derivative, you almost have the same function. Yes, the exponential function, absolutely. Okay, so the unknown solution for y has to be, now we're talking about the non-trivial elementary function. Certainly y is equal to 0 would work, because y prime is equal to 0, and 0 plus 0 is 0. Yeah, we're not interested in that one. But the only other one is some exponential function, and here we need to express this as e to the mx, because you see, when you took the derivative, you came up with a constant here. Well, this m, when you take the derivative of e to the mx, you're going to have m times e to the mx. That's m times y. So the derivative will be of the form of k times y, or actually for that function, m times y. Okay? And that's exactly what they do here. And if you plug it back in, now this is, you think it's so much easier to do it the other way. But look, follow through. That would be a times y prime, which is m e to the mx, so a e m to the mx, plus b times e to the mx, because that's your supposed solution. Factor out the e to the mx, okay, because you got e to the mx in this term and that term. Factor it out, and that leaves you a polynomial expression, am plus b, okay? Now guess what? E to the mx is never, ever, ever equal to 0. If you think about the graph of e to the mx, it goes like this. If m is a positive number, never reaching 0, approaching 0 for very, very negative x's, but never reaches 0. If m happens to be a negative number, it comes down like this, and then approaches 0 as x gets very, 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 very large positive, but never reaches 0. So since it doesn't, we can then solve this, divide both sides by e to the mx, because it's not 0, and now you have am plus b is equal to 0. Hey, I can solve that. M would have to be minus b over a, which is exactly what we set up here the k was. Okay? Now, boy, they go on and on with this. Okay? So let's put some actual numbers in there. Okay? 2y prime plus 5y, constant coefficients, linear equation, homogeneous equation. This again is just first order. Not necessarily go through that. All you have to do is say 2m, well, okay, your assumption is y is equal to e to the mx. You know when you take the derivative, you're going to have an m in front, so you get 2m plus 5 is equal to 0. Solve that, and you get m is equal to minus 5 halves. Plug that in. There is a solution. Okay? Now, and it's good everywhere because e function is defined for all values of x. Okay? It's a solution of that equation. The general solution would then be y is equal to some arbitrary coefficient, arbitrary constant, c1, e to the minus 5 halves x. Okay. So that was in a linear case. Okay. It worked beautifully. So what if we have a is a first order case? What if we have a higher order differential equation? But again, all the coefficients are constants. A sub n, y, the nth derivative of y plus a sub n minus 1 times the n minus first derivative of y plus count on down till you get a sub 3 times the y triple prime plus a2 plus y times y double prime plus a1 times y prime plus a0 times y, and that's all equal to 0. Well, guess what? The same thing applies. Since all these coefficients are constants, not functions of x, then you can say, hey, let's make that same assumption. Let's let y equal e to the mx. Okay? Now, oh, and by the way, this a sub n here is the only one that cannot be 0. Otherwise, if that was 0, that is not an nth order differential equation. It's an n minus first order differential equation. So if it's going to be an nth order differential equation, a sub n cannot be 0. The rest of them can be any number in the world. A sub n can be positive, negative, fraction, decimal, rational, irrational. It doesn't matter. We want them to be real numbers. It can't be 0. The others can be any real number. Positive, negative, fraction, decimal, rational, irrational, or 0. The others can. This one, all of those except 0. So all those can be anything, any real number, all those a's. Okay? The only restriction is a sub n can't be 0. Now, what we call then is when we do that substitution. Now let's take it back to just a second order differential equation. Let me scroll this on up so you can't see it, but that thing keeps popping up there. So let's get this to the top of the page. Okay. Let's start with the second order differential equation. A y double prime plus b y prime plus c y equals 0. We're not using the subscripts n's here. We're just using 3 letters, a, b, and c, okay, as our constants. Those are all constants. A is not 0. If we try to find the solution and again make that same assumption we did before, y is equal to e to the mx. Well, y prime would then be m e to the mx, right? Y double prime would be m squared e to the mx, okay? And that's exactly what you see here and here. Then when you plug that back in here, you have a times y double prime m squared e to the mx plus b from here times y prime, which is m e to the mx plus c times your y e to the mx is equal to 0. Every term has an e to the mx in it, right? Factor it out. That leaves you a m squared plus bm plus c times e to the mx is equal to 0. And again, just like we said before, e to the mx, the exponential function, is never, ever, ever equal to 0. So therefore, that's not going to ever produce a 0 here. So you can divide it out. You can, as long as it's not 0, you can divide by it. Do it. What does that leave you? That leaves you a polynomial equation. With the first order, it was a first order different polynomial equation, first degree polynomial equation, linear. This one happens to be a second degree, quadratic. Now this thing right here is called the auxiliary equation. Okay? No more differentials here, no more derivatives. It's just a polynomial equation in those 3 constants and the one variable, not x, but m, okay? The m now is, we're treating sort of like it's a variable. We're trying to find that coefficient, those undetermined coefficients, okay? In the introduction, we argue that because that's not equal 0, it's apparent, blah, 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 okay? So here is your equation that you're fiddling with. am squared plus bm plus c is equal to 0. Now, if you were given an equation like that, think back algebra now. You don't have to think differential equations. You don't even have to think calculus. Just think algebra. What would you do to try to solve that equation? Give me a couple of techniques. If y'all had been in my classes, lower level classes, when I'd ask a question like that, and I hope no one's offended at this. If you are, just let me know. I'll not say it anymore. But I would say, what's the F word? And you better give me the word factor. If this is a factorable quadratic, factor it, okay? You know how to factor quadratics if they're factorable. They're not all factorable, but if it is, factor it and see what values of m you come up with there, okay? Oh, here comes Dawson. Let's see if I can let him in. Okay, Dawson is here. Okay. Okay, Dawson's still connecting to audio. Yeah, it seems like he's here. Dawson, can you hear me? All right, good deal. We're in chapter 4, which is higher order differential equations, and we're just starting 4.3, which is homogeneous linear equations with constant coefficients. And let's just do a little quickie review. Higher order means beyond linear. So the one we're looking at right now happens to be a second order differential equation. Constant coefficients, a, b, and c, are not functions of x. Homogeneous means the whole equation is equal to 0. Linear, of course, means you don't cross any of your y terms. You can't have a y squared or y prime squared or y double prime squared. You can't have a y double prime times a y or a y double prime times y prime or y prime times y. You can't have anything like that. They all have to be linear. First order, your y and all its derivatives, you can't cross them up. So that's what we're dealing with. And we just have said that when you have an equation like this, your first assumption is let y equal e to the mx. Because think about it, that's the only function that when you take it, its derivative, all its derivatives, they all look the same. They all have an e to the mx in them. Yeah, when you take derivatives, you get m's in front. Well, that produces what we call the auxiliary equation. You can follow through what we did here, and we'll wind up with this quadratic equation, because this is the second order differential equation. And what we're just saying, how do you solve that? Don't think calculus, don't think differential equation, think algebra. You factor it if you can. What if you can't factor it? What's your fallback? Quadratic formula. You know how to do that. Minus b plus or minus square root of b squared minus 4ac all over 2a. Yeah, you remember that. If not, remember it. Okay, and there it is right there in case you need to see it. That last equation, this is called the auxiliary equation of that differential equation. All you do is make this assumption, y is equal to e to the mx, and then you can go through doing all those y prime and y double prime, but you don't really need to. Just do a m squared plus b m plus c and set that equal to 0, because that's what it always comes out to be. Now, they're not even messing with factoring. I like to mess with factoring because it's easier. Okay, but once you have this auxiliary equation, you may, and you do the quadratic formula, you have two, let's see, no one was trying to get in, were they? No, we got them all here. Again, I'm going to scoot down here because I keep hitting that at the bottom of the page. Here are the three cases you might wind up with that auxiliary equation. If you use the quadratic formula, you wind up with m1 b minus b plus the square root of b squared minus 4ac. All that is over 2a. Or the second one is m2. The second, oh, here comes Ricky. Good deal. Good to have Ricky here. Okay. So we're missing the two C's now, Corbin and Cole. Okay. Now, I think in an email or something, Cole said he had been sick this summer, so that's one reason he hadn't been here much. He was here Thursday, so I'm hoping he'll get back today. But anyway, let me see. Ricky, are you able to hear us yet? Okay, good deal. We're in Chapter 4, Higher Order Differential Equations, Section 4.3, which is homogeneous linear equations with constant coefficients. Okay, and I can't go over the whole thing with you, but the bottom line, as long as every coefficient is constant, and homogeneous means that differential equation is equal to 0, linear differential equation, your assumption is y is equal to, this is your assumption, y is equal to e to the mx. Because that's going to work in every derivative. You're going to get an e to the mx, and then they're all going to be constants. You can have m's and m squareds and m cubes or whatever, but they're all going to be constant coefficients. So that's your first assumption. Then you plug those things in and you come up with what we call an auxiliary equation, which is merely, and here's why you can do this, e to the mx is never, ever, ever equal to 0. And remember, we have this differential equation equals 0, homogeneous, okay, equals 0. So your e to the mx can factor out of every one of those terms, and that leaves you a polynomial. And if that polynomial happens to be a second degree, a quadratic, you can use the quadratic formula to come up with a solution, because if e to the mx can't be 0, that means that quadratic expression has to equal 0. When you set that up and use the quadratic formula, you'll get one solution. Now your variable here is now your m, e to the mx. That's your variable here, the thing that's being squared. So the first one is minus b plus the square root of b squared minus 4ac, all that over 2a, and the second one is m2 is minus b minus the square root of b squared minus 4ac, all over 2a. Now, if you go way back to algebra, sometime in your long distance past, when you did algebra, you know when you have a situation like that, you have three possible cases. The first of these is that m1 and m2 are both real and distinct roots. m1 could be 7, m2 could be minus 3. Okay? Any two real numbers. Well, that meant you could have factored that quadratic. You didn't have to use a quadratic formula. You could have factored it and come up with m1 equals something, m2 equals something. So there's your first case. Hang on to that one. And when is that true? That's true anytime this thing inside the radical, and if you remember way back somewhere in your long distance past, you called that the discriminant. If that discriminant is positive, then you're going to have a real root. Okay, because you can take the square root of a positive number. Okay, and if that is positive, a real number, okay, positive real number, even if it's a radical, that's fine, you will have two roots. You'll have an m1 when that is, you take whatever the square root of that is, as long as that's a positive number, you can take a square root, subtract b from that, and divide it by 2a, that gives you a number. But over here, you do minus b minus that real number, square root of whatever that positive number is, and divide that by 2a. So you get two totally real, totally distinct numbers anytime that discriminant is positive. Now, what if that discriminant was 0? Then you get the same thing, minus b over 2a. Minus b over 2a. If that discriminant is 0, you're not adding or subtracting anything. So you have two real solutions. They're just the same number. We called it a multiplicity of 2. You had two real numbers. Saw a squirrel playing in the tree out there. Sorry, I got distracted. Okay, so there's the second case. If the discriminant is positive, you have two real distinct roots. Okay, if they happen to be, if that discriminant is 0, you only have one. You have two real roots, but they're the same numbers. Okay, hang on to that one. And then if m1, okay, if that discriminant is negative, if that's b squared minus 4ac under that radical is negative, you don't have any real roots. Okay, and back in algebra we used to say no real solutions, right? Well, now we say we have two complex solutions with imaginary parts, because you have a negative under the radical, but they happen to be complex conjugates of each other. Okay, so m1 and m2 are two complex numbers. Well, all numbers are complex numbers, but they have imaginary parts, but they're complex conjugates of each other. So let's take the three cases separately. First one, two real distinct roots. Okay, what do we do with that? We just plug them in. One solution is going to be e to the m1x, where m1 is one number. I said before 7, e to the 7x, and y2 may have been, like I said, that m could have been minus 3. That would have been y2 is e to the minus 3x. Two completely distinct and independent solutions. We see those functions are linearly independent, all real numbers. Okay, hence they form a fundamental set. So all we have to do is go to our general solution, y is equal to C1 times M1, e to the M1x plus C2 times e to the M2x. There's your solution right there. Done. You have solved your first higher order linear homogeneous differential equation. Okay? You first find that auxiliary equation, factor it if you can, come up with M1 and M2 if you can, fine. If it won't factor, use the quadratic formula, come up with M1 and M2 if you can. As long as that discriminant is positive, you're going to get two real distinct solutions. But what if we have that second case where M1 and M2 are real, but they're the same number? They're equal to each other. That's when the discriminant is 0. You just have M1 and M2 are both minus b over 2a. That's it. That's all you got, okay? Now, you get one solution, y is equal to e to the M1x or M2x. They're the same number, okay? But you can't just then do a second one because those are not linearly independent. They're the same. So from that quadratic formula, the M1 is minus b over 2a, since I've already said it. So here, but we have M1 equal M2 because that discriminant was 0. Now, remember we did that section 4.2 last time. It was very short, but we went over the way to come up with a solution given one solution and you can't see how to get the second one. You go through that rigmarole that we did, and what they called it was reduction of order. Okay, and it was a mess. Okay, it was a lot of stuff, but what we wound up with, that the second solution, y2, was the first solution, y1, times the integral of, if you go back a page, you'll see our general case there. Boy, they don't show it too well. Let me just go back real quickly and show you, in case some of you weren't here. So sorry, this will take just a few minutes to go back and get this. Okay, here it is. There was your solution. Now this was if you had one solution, didn't know how to get the second solution. Okay, I'm going to have to scroll up till you can see everything that's going on here. Hopefully you'll be on the same page. Ah, here we go. Well, not quite. Yuck. Not going to show it all. Okay. But anyway, here was your second order differential equation. Y double prime plus, now they're calling it P, Y prime plus QY. And that was equal to 0. Okay? Now, what they said to do, if you knew one solution, and that's what this was, Y1, you know it. Here's what we came up with. The second solution, your Y2, would be the Y1 times the integral of, there's an E again, e to the minus integral of px dx. Now this was if this was a function of x. Remember now we've got a constant function. So this would just be the integral of a constant, okay, dx, okay, and e to the minus that, okay. And then you would put your y1 squared down here, okay? So that's what we're doing. Remember now, the numerator here is e to the minus the integral. That looks a lot like we did when we did the integrating factors for linear equations, right? Except we didn't have the minus sign. That's the big difference. And then you divide by y1 squared inside the integral. y1 is outside the integral here. y1 squared is inside. Now again, remember y1 is a function of x. It's e to the mx, something or another, okay? So we can't say, oh, that's a constant too. No, it's not. It's a function of x. But the p is a constant. All right, so let's scroll down here and apply that solution we got called a reduction of order, and let's do it here. And we may have to go to a white page to do it. So let's do that if we need to. Okay. We'll get there in a minute. Okay. We're working on case 2 here, repeated real solutions. Okay. And maybe I ought to keep my equation there. Let's see if I can keep it there. Nah, I don't think I can. Okay. Not enough room on the page. But I'll write it down when we get to the... Okay. So let's go to the whiteboard. We still got 4 people here, and that's what I got. Okay. We'll go to the whiteboard here. Now I got to get this mess out of the way. You can't see it, but I can. It blocks what I'm trying to do here. So it's up here. And then let's also, let me move the whiteboard as much as I can to give me as much white space as possible. Okay, I think that's about it. All right. So let me write down as much as I can here what our original equation is. Okay, I'm going to write it down in sort of gory detail here. We got A y double prime plus B y prime plus C y is equal to 0. A linear differential equation with constant coefficients, second order, homogeneous, is equal to 0. Okay, our assumption here is let y, and this will be for every one of these things, okay, equal e to the mx. Okay, and when you take the derivative of the guy, you get m e to the mx. You take the second derivative, you get m squared e to the mx. So your differential equation becomes a m squared e to the mx plus b m e to the mx plus, not writing well, plus c e to the mx is equal to 0. And like we said before, I'm doing this for those who came in a little bit later. You can factor out e to the mx. You have it in every term. So let's factor it out. E to the mx. And what do you have left? am squared plus bm plus c, that's equal to 0. And guess what? E to the mx can never, ever, for any value of x, ever be equal to 0. It's always a positive function, whether you're a positive m or a negative m, it doesn't matter. It never reaches 0. It's always positive. Okay? So therefore, we can divide it out. Because it's not 0, we can divide it out. It will never be 0, so it won't ever solve this equation. So what we have here is what we call the auxiliary equation, that right there, am squared plus bm plus c is equal to 0. And then from the quadratic formula, we know that m is equal to minus b plus or minus the square root of b squared minus 4ac, quadratic formula, classic standard form, all divided by 2a. Now, what if this discriminant was 0? That's what we're dealing with now, case 2. If that discriminant is 0, b squared minus 4ac is equal to 0, you have one and only one real solution, and that would be, if this is equal to 0, you have minus b over 2a. But you know you got two solutions. It's just a double solution, multiplicity of 2. So that gives you, go back up here, and we have that your y is equal to, or let's see, let's not do it there. Okay, let's do it here. y1, your first solution, is equal to e to the minus b over c times x. No, b over, goodness gracious, where did I get that? All right, where's my eraser here? Come on, there it is. Minus b over 2a. Yuck, I hate this eraser. Okay, minus b over 2a. Okay, so there's your solution. Now, we don't have to call it that. We could just call it M1. Okay, so that'll be a little easier. That just, it helps us a little bit. Let's just do that. Equal e to the M1x. Okay. It happens to be M1 happens to be minus b over 2a. Okay, but there's your first solution. Now, in what we just did, if we are looking for the second solution from that reduction of order, remember we said that y2 is equal to y1, which is exactly this thing, times the integral of e to the minus, now what was that? That was your b. So we might want to get back that in here. So this was e to the minus b x, I believe it was. Okay, now don't confuse this with that. Okay, this is a completely different deal here. Your p of x is b, so I'm sorry, I forgot to put my integral. I knew I was missing something. E to the minus integral of bx dx. Okay, now that's not an exponent. My pen is just not writing well. Let me see if I can get that erased so it makes a little more sense now. Oh, I erased too much, but that's okay. E to the minus the integral of b dx. Okay, that's a little better. Okay, divided by your y1 squared. Well, that's e to the 2. Let's go on and put what the m is. I think they do it. Let me make sure. Now they leave it there. So, okay. They wait to put it in. I was going to go on and put it in now, but let me stay with what the book has. Okay, I erased too much, but we can rewrite that. Okay, e to the 2m1x. Okay, and this out here is e to the m1x also. I'll put that in the next step. Well, what is the integral of b? Okay, this will be y2 is equal to, I'll put it in now, e to the m1x, that was your y1, times the integral of e to the, and what's the integral of bx? That's minus bx. Okay, we don't do any plus c's with that. And divide that by e have I done something stupid here? I think I did. I think I put the wrong thing in. Your P here, P of X, no, that's B. That's right. Okay. Okay. I can't quite figure out how they wound up with that being an M. Let's go over here and scratch a little bit and see, where is my pen? There it is. Okay, remember here we have M1 is equal to, yuck, minus, come on back. Okay, here it is. Minus B over 2A. That's what M1 is. So let's get what minus B is. Minus B is M1 2A M1. Okay. Now, they have just 2M1, not 2AM1. What in the world have they done with the A? Okay, I cannot see this at all. Minus B would be 2. Okay. It may be they're assuming A is equal to 1. I don't know why they're making that assumption, but okay, no, I'm sorry. They did it the other way. Okay, I think they did it right. Okay, so they're basically saying okay, they're saying 2M1 is equal to minus B over A. There's a minus sign there that didn't draw. Okay, so I still don't quite see how they lost it, but they did. Oh, of course. Sorry about that. That P that we had here, okay, sorry about this. The P that I said was minus B, that's not minus B. Remember? Okay, remember the P when you were doing this, you always did divide by A. The first thing they did was divide this by A. Now this was in on the previous page. Divide everything by A. Okay, so that makes your M1 2. Okay, because that's why they got B over A here. So the M1 is that. So this is not minus B, this is minus B over A. Sorry, that's what I forgot. This thing here, your P here was B over A. Okay, so you get, using that substitution then, sorry about that. Can't get my pen to move, there it is. Okay. This substitution, this then would be M1. All this just to get to this point. M1, 2M1 over 2M1x, and this we had was 2M1x dx. I left that off here. Okay, and of course this is 1. So what do we get y2 to be? This is what the whole reason for doing this. This is equal to x. The integral of dx is just x, so it's x e to the m1x. Okay? Remember we only had one m1? Here are our two solutions. y1 was e to the m1x, and y2 is e to the x m1x. So basically, you go back here and plug them in, your general solution, then would be y is equal to C1 e to the, and let's see what they leave it M1. I would have put minus b over 2a, but we'll do it M1, M1x plus C2x times e to the M1x. Whatever you've got that solution to be, m is equal to minus b over 2a. That's just a number. The first solution is C1 e to the mx. The second one, because you only have one m, is C2x e to the mx. So that's how we handle it when we have a repeated root. Okay? And let's go back here, and you see that's exactly what they got here. Y is equal to the general solution, C1 e to the m1x plus C2x e to the 1x, e to the m1x. It's only one m, not two m's like we had before, but we have two functions with m in it. One is e to the mx, the other is x times e to the mx. And those are linearly independent. All right, if you thought that was a pain, wait till you get to case 3. Now, case 3 goes into all kinds of convoluted things here, and rather than bog us down with all of the details here, we're basically going to go to the bottom line. But just to give you a flavor for it, what if that M1 and M2 are complex? Well, of course they're complex. Complex with imaginary components. In other words, that conjugate discriminant was negative. So you're going to have an I in it somewhere. Okay? Now, here are our two solutions then. Written in a really strange way. M1 is alpha plus I beta, and M2 is alpha minus I beta. Now, what in the world are these alphas and betas from? If you think about your quadratic equation, let's see if I can do it over here with, I don't think I can. It's not going to let me write, is it? No, it won't. So, yuck. So I'm going to have to go back to the white page. Okay, whiteboard. Okay, and I need to clear all those. Now, well, I should have kept some of them, but let me remind you of what we wound up with. We wound up with m is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Okay, now we're assuming this thing is negative. So what we have then is something like this. Minus b over 2a. That's a real part. That's what we're going to be calling the alpha. Okay? And then we have plus or minus I times the square root of, remember this is negative. Not zero, not positive, negative. Well, if that's negative, then for a minus b squared, for ac minus b squared must be positive. If this one's negative, reverse the order and you get a positive number. Well, that is some real number. Okay? Maybe messy, but it's still a real number. So that's where we get plus or minus. This becomes our beta. So that's where you get plus or minus I beta, or beta I. That's what the alpha and the beta are. We're not going to use them as such necessarily, so don't sweat them for yet. That's what the alpha and beta is. Rather than writing minus b over 2a every time they want to write an alpha, they just write the letter alpha. And rather than writing the square root of 4ac minus b squared every time, they just write beta. So those are our complex solutions to the quadratic formula. Okay, so let's go back to here, and that's where this alpha and beta come from. Alpha plus I beta and alpha minus I beta. Remember, it was alpha plus or minus I beta. So one of them's a plus and one's minus. There's your M. Two distinct solutions, but they're complex conjugates of each other. Okay. Now this is of the auxiliary equation, the M's. Okay, so you have two M's. Now, they remind you of several things here. The alpha and beta are both okay. The beta is positive here. Alpha is not necessarily positive, but beta is. Just to remind ourselves that beta has to be positive. Let's go back to here, and hadn't thought of this, but that is a positive number. Okay, has to be. I mean, it's the square root of a positive number. It's a positive as a principal square root. The plus or minus are taken care of here. Beta is a positive number. Alpha could be positive or negative. Now, I don't know why they make a deal about it here, but since they said it, I wanted to reinforce that. Okay. Now, they're both real numbers. Alpha and beta are real. And I, of course, is the square root of -1, which means I squared is -1. Now, formally, there's no difference in that case in case 1. Here would be your solution. Y is equal, now they put a capital C1. I don't know why, but they do. Capital C1 e to the M1, which is alpha plus I beta x, plus capital C2 for some reason, e to the M2, which is I minus alpha minus I beta x. Those are your solutions. Okay. However, they're covered up with complex numbers, with imaginary parts in them. In practice, we prefer to work with real functions instead of complex exponentials. Yay! Now, Euler's formula. I don't know if y'all remember this from some long distance past calculus course. You may not have ever hit it. Euler was an incredible mind. One of the most prolific writers of mathematics ever. Okay, he came up with this formula that relates e to the I theta, okay, which would be this part here, e to the I beta x, here and here. He relates that e to the I theta as cosine theta plus I sine theta. Amazing but true, and I'm certainly not going to go through and tell how he formed that. That's the truth. Okay, now what we have here, the i's, e to the i's always show up with your beta x's here. So where theta is any real number, okay, now if you really want to dig into it, the formal derivation of Euler's formula can be obtained from the Maclaurin series. E to the x is equal to this thing right here, and substituting instead of x, I theta, plug it in. Remember, the I squared is -1, I cubed is minus I, and so on. Then separating the series in the real and imaginary part, blah, 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 you can get down to this. Okay, that really gives it to you. I don't want to go there. If you do, knock yourself out. It works. I've done it before. I've seen it done before. And it truly does work. Okay. If you've ever done the Maclaurin series with cosine, they all come up with positive exponents for n's, and the sines come out with, cosines come out with evens, sines come out with odds, and because of that changing of signs of your i's and I squareds and I cubes and all like this, you alternate signs, and the e doesn't have a sign change, and it's just all the powers of all the n's are in there, and it does come out that does break down exactly like it's stated here. that only gets you a tip of the way through what we're going to do. So the e to the I beta x that you have here and the minus I beta x here, this will give you cosine beta x plus I sine beta x. Instead of I beta x here, you have theta instead of beta x. So it'd be cosine beta x plus I times the sine of beta x when this is the positive here. For the negative, you have cosine beta x, because cosine's an even function, so that doesn't change the sign. But sine's an odd function, so you change that to a minus I sine beta x. All right, it's just getting worse, isn't it? Okay, does this seem to be helping any? Really not. Now, yeah, we used here that cosine of minus beta x is the same as cosine of beta x, because cosine is an even function, but sine of minus beta x is minus sine of beta x because sine's an odd function. And then if you were to add this equation to that equation, okay, so e to the I beta x plus e to the minus I beta x, look at what happens. You get 2 cosine beta x because these two cancel out. But then if you turn around and subtract this one from that one, then your cosines subtract away and you have 2I sine beta x here for that difference. Now, remember, this was our original formula here. This is our original solution here. And here's they go and do it again. And this kind of bugs me, but it works, so it's okay. This is true for any choices of constants C1 and C2. And they say, well, let's let C1 equal C1 and C2 be the same and equal to 1. And then let's turn around and let them be the opposite and let them equal 1 and minus 1. Okay. If you plug that in, my goodness, here, and work that out, that is when the two are equal, and this is when the two are opposite. You get this one. So there's a y1 and a y2. Those are two separate solutions, distinctly separate solutions. Okay? Now, combine those. y1 is equal to this. Plugging this thing here, 2 cosine beta x in there, you get 2e to the alpha x times cosine beta x, and plugging in y2, this, you get e to the alpha x times this difference here, which is 2I sine e to the alpha x sine beta x. I would have put the e to the alpha x out front, but they didn't. Okay. All right. We have a y1 and a y2 now, but that y2 still has an I in it. I thought we were going to try to get rid of that. Well, let's move on down a little ways here and see if we can do anything about that. Now, if you go way back, not that far back, but corollary A to theorem 4.1.2, which is way back in 4.1, we're in 4.3 now. Go back and look at that. The last two results show that e to the I alpha cosine beta x and e to the I alpha sine beta x are both real solutions. Now, I don't know if you remember that, of 2. Moreover, those solutions form a fundamental set on minus I to I, and therefore we've lost. Somehow, magically, they got away from the i's. So here's what we have then. Here is your bottom line. If you have your discriminant being negative, so you have complex solutions, you do the same thing that we did before, but the alpha is the real part of that solution. Beta is the complex part of the imaginary part of the solution. And you wind up with C1. Now this is a little c, not the same c as before. And this is an arbitrary coefficient now. You don't assume anything here. Okay, any coefficient, e to the alpha x cosine beta x plus c2, some other arbitrary coefficient, e to the alpha x times sine beta x. Well, they both have an e to the alpha x in them. Pull that to the outside, and you have then a c1 cosine beta x plus c2 sine beta x. No more imaginary parts, none whatsoever. You just have to remember what the alpha is and what the beta is. It comes out of the solves pretty nicely. You now have real functions of cosines and sines, which you know are linearly independent. Yeah, you have the e to the alpha x in front. That's fine. Okay. The alpha, the beta, they all come from your quadratic formula. Those are fixed with whatever things you got in the problem. The C1, C2, those are your arbitrary coefficients. Okay? Is this making sense? I know this is awfully blah, blah, blah-ish. But let's do what they have us do here. Let's solve these three differential equations. We'll start with A. So let me go down back to my whiteboard and clear it out of the way. We won't need it, any of that yet. And let me set this aside for a moment so I can write down the problems reasonably. Well, I can't do it without this, okay? Here's what we got. Okay, 2y double prime minus 5y prime minus 3y is equal to y is equal to 0. A linear, homogeneous, second order differential equation with constant coefficients. Now, I like to write this down. The book tends to forget to do it or not do it. Here's my assumption. Let's assume y is equal to, this is your solution, is equal to e to the mx. I always like to write that down. That gives us now, you don't have to put that as part of your solution if you don't want to, as part of your problem if you don't want to. Basically, you can go straight to the auxiliary equation, can't you? That would be 2m squared minus 5m. Does anyone not see why this is happening? Minus 3 is equal to 0. Does everybody see how that comes about? You can go back and take the first derivative, second derivative. We've done that before, and it always came out with this coefficient times m squared, because that's the second derivative, minus that, with that coefficient times m to the first power, minus this because you don't have any m's left in there, okay? And that's equal to 0. There's your auxiliary equation. What we need to do is see if we can come up with solution for that quadratic equation. Forget calculus, don't forget it, but for now, you're back in algebra, okay? Let's see if we can factor that. I don't know if we can or not. Let's see if we can. It would have to be a 2m times an m, right? That would be the first factorization. This is equal to 0. And then you have to have opposite signs. So I'm just going to put plus and minus, see if they work. And let's do a 3 here and a 1 there and see what happens. 2m times m is 2m squared. That's okay. And this would be a minus 2m plus 3m. That goes, oops, that's not going to work. Okay. Obviously, that will not work. Now, if I can get it up here to my eraser, I'm going to erase that mess. Okay. Okay. So let's try something else. Let's put the 3 over here and the 1 here. Now let's do it. 2m times m is 2m squared. Now you have a minus 6m plus m. Sure enough, that's minus 5m minus 3. We have our solution. So, what is your y? y1 is equal to e to the, oh wait, I guess, I like to jump steps here, but I shouldn't do that. First time we do it anyway. We may skip steps later. Okay, let's go back and do it. Okay, this would give us m is equal to minus 1/2. Can I skip those steps? Are you okay with that? And this one gives us m is equal to 3. Tell me, are you okay with skipping those steps? Plug in a minus 1/2 for that m, you get 2 times minus 1/2 is minus 1 plus 1 is 0. Plug a m3 here, you get 3 minus 3 is 0. So both of those will work. So now we plug and get our solutions. Your general solution, y, is equal to some arbitrary coefficient 1 e to the minus x over 2, that's with a minus 1/2, plus some other arbitrary coefficient c2 e to the 3x. 2 linearly independent solutions. That's it. That covers every possibility for you. Okay? You might say, wait, I thought the trivial case always worked. Yes, it does. Well, then you'll choose C1 and C2 both equal 0, and you get y is equal to 0, and that certainly does work. So you've covered all your bases here. Any choice of C1, C2 is going to give you a solution. And how did they do in the book? Y is equal to C1 e to the minus x over 2 plus C2 e to the 3x. Perfect. Now, I did too much talking there. Do y'all understand what I did? Are there any questions whatsoever? This was case 1, 2 completely independent solutions. We could have done the quadratic formula. It's just a little harder than factoring. Sometimes you can't factor, you've got to do the quadratic formula, okay? But if you can factor, you get the same things, okay? All right, to clear? All right, I'm going to clear that one, and let's do the second one, the B one. This one is y double prime minus 10y prime plus 25y is equal to 0. What's our assumption? Let y equal e to the mx. The book doesn't usually do this. I like to always put it in because I want to remind myself that's what we're going back to. Okay, now we can write down the auxiliary equation. Can someone tell me what it would be? Anybody? Anybody? There it is. Y'all are really talkative today, aren't you? All right. What's the first thing you want to try? Quadratic formula or factoring? Y'all are really quiet. I'm going to try factoring because I know exactly what it factors to because I'm used to seeing that form. Well, the only possible factorization for m squared is m times m. And since you have this positive sign here for this one, that means these two signs have to be the same. And since that one's negative, they both have to be negative. Now, when I ask myself what's the only possible factorization of 25, there's only a few. I'm going to go with the simplest one, 5 times 5. Let's see if that works. M times m is m squared minus 5m minus 5m, that's minus 10m, plus 25. Yes, that works like a charm, but guess what you got? Only one solution. M equal 5 and m equal 5. Okay, it's two solutions, but they're the same number. So you have one possibility. Y1 here is E. Yuck. I hate it when it does that. Is e to the 5x. Okay? Now, remember what we did for case 2? And this was pretty easy. Y2, you can just write it down now, is equal to x e to the 5x. Remember, it's just multiplying it by x. That's what the case 2 gave you. All that we went through to get there, that's what we got. So now your general solution is simply y is equal to c1, some arbitrary coefficient, e to the 5x, plus c2 times x, e to the 5x. There it is. Look in the book and you see y is equal to c1 e to the 5x plus c2x e to the 5x. That's what you do when you have your discriminant is 0. If you had done the quadratic formula, you come out with a double root. You do the first one just as you would normally do, and then put a factor of x in front of the second one. Give it a different constant. That was pretty easy. Any questions on case 2? See, all the blah, blah, blah about how to get there, that's one thing. When you actually do them, they tend to be a lot simpler. Okay? Ready for case 3? Clear the drawings there. And here's the third differential equation. How are we doing on time? I think we're okay. See, we go to 10:45, right? So we got an hour to go. Let's get this one done. Y double prime plus 4y prime plus 7y is equal to 0. Okay, this book is getting hot. I'm going to get it off of my lap. Okay. Now, our assumption always is let y equal e to the mx. Always for these linear, higher order linear differential equations with constant coefficient, that's what we assume every time. And guess what? It's going to work. Hopefully every time. Okay. So let's see what we've got now. Auxiliary equation. You could take derivatives of it, plug in, but you know what it's going to turn out to. It's going to turn out to m squared plus 4m plus 7 equals 0. Now, who wants to factor that one? Ricky, I see your light on. I know you want to factor that, don't you? Not going to factor. No way in the world. 7's a prime number. Its only factorization is 1 and 7. All things are plus, so it has to be m plus 1 times m plus 7. No way you're going to get a 4 out of that in the middle. The b won't be 4. So since it won't factor, we go to our good old trusty, well now, yuck. Let me get my eraser. I think my finger must have hit something that it wasn't supposed to hit on the pen. And, okay, let's see if I can get by without doing that again. So here's what the quadratic formula tells us. M is equal to minus b, that's a minus 4, plus or minus the square root of b squared, which is 16. Are y'all following this? minus 4 times a, which is 4 times 1 is 4, times c, which is 7. 4 times 7 is 28, one of my favorite numbers of all time, all divided by 2a. A is 1, so that's just a 2. So what do we have here? Minus 4 plus or minus the square root of minus 12, am I doing it right? Divided by 2, which is minus 4 plus or minus. Now, the square root of minus 1, that's your I. So I'm going to pull out the I. Okay, that gets rid of the minus sign here. 12, those factors into 3 times 4. Square root of 4 is 2. So it's going to have a 2i there. But what you have left over is a 3. It's not a perfect square, so that's going to be root 3. Now, I can't remember if this book writes it that way or not. A lot of books like to put the whole real part in front and then the I afterwards. I don't like to do that after a radical because sometimes in my sloppiness I might think the I is under the radical. It's not. It's outside. So if I put it in front, there's no doubt. But this is all over 2, remember? And since there's a 2 in the numerator and denominator, this will become a minus 2 here, and this just becomes a 1. So our m is now, yuck, I hate it when it does that. Okay, m is equal to minus 2 plus or minus I times root 3. Okay, because the 2 went out of the denominator. Now, a quick reminder. The minus 2 here is what we were calling the alpha, and the root 3 is what we were calling the beta. Okay, so if you go back to your solution, remember what that was? Y is equal to, and this is a general case now, e to the alpha x, that's e to the minus 2x. No arbitrary coefficient with that one. It's just e to the alpha x, alpha is minus 2, minus 2x, times, parentheses, and then you have the cosine. This is where you put your arbitrary coefficients. C1 times the cosine of the beta. Well, the beta is root 3. Plus C2 times the sine of that same beta, root 3 times x. Now, here again, I don't usually like writing the radical in front. I would sometimes write it as x root 3, but that does get a little confusing. So as long as you separate them, make sure that the x is not under the radical, you got it. There's your solution. Hey, guess what? After all we went through and all the assumptions and all the arguments and everything else to get there, all those steps, there's your solution. That's pretty simple, okay, in a roundabout way. Let's see how the book did. They have e is equal to e to the minus 2x, there's your alpha, times parentheses c1 cosine root 3x plus c2 sine root 3x. Just a couple of notes here. That's always a plus sign in between. Don't ever think you have to change it and make it a minus sign. I can't get my pen. Oh, there it is. That's always a plus sign. Now you might say, well, what if this was a negative? Remember, beta is always positive. That's why they made that point earlier. The beta is always positive. So that's always going to be a plus sign there. Okay? Now, you okay with those? Any questions on how you do any one of the 3 cases? It turns out being way simpler than you ever thought. If that discriminant is positive, you have 2 real solutions. Even if you can't factor, quadratic formula will give you, if we had reversed these 2 numbers here and would have had a positive 12 under here, that still you couldn't have factored that, but that could be factored as 4 times root 3, so that would be, everything would come out the same except you wouldn't have the I here, okay? And then you would have 2 plus or minus, minus 2 plus or minus root 3. Well, those are two solutions. The first one would have been e to the minus 2 plus root 3, all in parentheses, times x, plus c2 e to the minus 2 minus square root of 3x, all that in parentheses. You'd have had two unique real solutions. Fine. Okay? So sometimes you can't factor it, but it still gives you two unique real solutions. Okay? If that discriminant comes up to 0, get that first one, the m, the only m you got, and then use the same m but do an x times e to the mx then. Okay? Done. And if that discriminant does come up negative, go through the work here, figure out what it is, identify your alpha, identify your beta, and then plug them into the formula. E to the alpha x, no arbitrary constant in front of that. Here's your arbitrary constant, C1 cosine beta x, beta is always positive, so plus C2 sine beta x. Done. Done. Absolutely taken care of. How about before we do example 2 on page 137, let's take a bladder break. Are y'all in favor? I just need to get up and walk some, and it won't hurt to go and take some pressure off. So I'm going to, please tell me, I know I started the screencast-o-matic. Let me see if I can find it here. Okay, it is recording. Click here to pause. All right, minimize this. Okay, can you hear me? Anybody? Yay or nay? Oh no, don't tell me. Okay, is anyone watching? Can you hear me? I see Ricky's. You can. Okay, good. The only reason I said this, it happened last Thursday and it happened again yesterday. Right in the middle of teaching, the microphone went off and I had to get rid of the headset, put it aside. I was telling them earlier, my wife managed to get them working both times, but she went to the office to work today, so if it goes out, I'm back using the microphone on the computer. Okay, so let's pick up. Any questions up till now on anything we've done? Okay. We just finished example 1 on page 137, parts A, B, and C. Let's move to example 2. Example 2 is an initial value problem, and if I can get the pen to move here, there we go. We'll clear the drawings and do this one. Here's a differential equation. 4y double prime plus 4y prime plus 17y is equal to 0. But this has an initial, two initial values. Don't have room to do them, so I'll have to drop down a little. The first initial value is at y of 0, and this truly is an initial value then, is equal to -1, and y prime at 0, which makes it an initial value problem. Both the derivative, the function, and the derivative are evaluated at the same value. Otherwise it would be a boundary value problem. This is equal to 2. Doesn't matter what the right hand sides are, but the thing in parentheses has to be the same. All right, now remember what our assumption is. Our assumption is this is a, come on, oh, there we go. This is a linear, homogeneous, second order differential equation. Okay, so our assumption with constant coefficients, that's required, constant coefficients. So therefore, our assumption is let y equal e to the mx. That's always it when you have constant coefficients, linear, homogeneous, first or second or higher order differential equation, or first, yeah, e is equal to e to the mx. Okay, now that gives you your auxiliary equation. Anyone want to tell me what it is? For m squared plus 4m plus 17 is equal to 0. Anyone want to try to factor that one? Again, 17 is a prime number, so only factorization be 1 and 17. I don't think there's any way in the world you're going to factor that and get a 4m as a middle term. 4 as a middle coefficient. Not going to happen. So we have to go to the quadratic formula, which is simply m is equal to minus b, in this case 4, plus or minus the square root of 16, 4 squared, b squared is 16, minus 4 times a times c. I'm not going to do that one in my head, okay? I can't do that one in my head. I could look in the book, but I'll pull out my calculator, and it's my telephone, so I have to get into it and do 16 times 17. 272, is that what y'all got? 4 times 17 is 272. All over 2 times a, that's 8. 2 times 4 is 8. All right, let's see what we get now. That's a minus 4 plus or minus the square root of a negative 256. I think. Is that what y'all got? Over 8. Okay. Let's string that out a little more. Minus 4 plus or minus. Okay. Now I'm going to pull the I out. I know. The minus 1, square root of minus 1 is I. So that's on the outside. Now I know 256 is a perfect square. I think it's a perfect square of 16. Okay. Let's just check and make sure I've done everything right. Subtract 16 from that, and you get that. And take a square root of that. Yep, that's the square. The 16 is the square root of 256. Okay, so that would be then minus 4 plus or minus, pen, come on over here. Okay, there you go. Plus or minus 16i. Okay. All over 8. Is that what y'all got so far? Now let's split it up to a real and imaginary part. The real part is minus 1/2. And the imaginary part is plus or minus 2i. Okay, and that tells you right now the alpha is minus 1/2 and the beta is 2. Okay, we can write down our solution. Well, first stab at the solution. The general solution would be y is equal to e to the alpha x, which is e to the minus x over 2 times, open parentheses, c1 cosine beta is 2, 2x plus C2 sine of 2x. There's your general solution. But we have an initial condition. That initial condition is when x is equal to 0, y is equal to 1. So or negative 1. So let's put the minus 1 for y is equal to x equals 0. Well, e to the 0 is 1. So that's easy. And then we have cosine of 0 is also 1. So that's C1. Sine of 0 is 0. So we have minus 1 is equal to C1, which implies that C1 is equal to minus 1. That's exactly what it says. So let's take that form. Y is equal to e to the minus x over 2 times minus cosine, because we know C1 is minus 1, minus cosine of 2x plus C2, we haven't determined that one yet, sine of 2x. Okay, now we need to take a derivative here, don't we? Ooh, yuck. Where will I do that? Where is my cursor? Come on, cursor, show up somewhere here. There we go. All right, let's try to do a y prime. Y prime is going to be equal to, you have a product rule. So it would be the first, e to the minus x over 2 times the derivative of the second. Well, derivative of cosine is minus sine, so that's going to change that to a plus, but then you have a chain rule for a 2. So that looks like it's going to be a 2 times the sine of 2x. Do y'all follow that so far? Then plus C2, said C2 and wrote 2, C2 times the derivative of sine is cosine, but then you have a 2 in front, so it's 2 C2 cosine 2x. Now we had to take derivative because that's our second boundary value, our initial value. Okay, so when we plug in a 0 for x, we get a 2 for our y prime. So we have a 2 is equal to, well, e to the 0 is still 1, so that's not going to enter the picture here. 2 times 0, sine of 0 is 0, so that's going to disappear. And then you have a 2 C2 times the cosine of 0. Cosine of 0 is 1. Okay, so that's just going to be 1. Well, it looks like to me that C2 has to be 1. So our solution, one and only solution, y is equal to e to the minus x over 2, that doesn't change, times your C1 was a minus 1. So I really want to put the sign first, so I'm going to write it first. I'm going to put sine, I know the book doesn't do this, of 2x minus the cosine of 2x. That's what my take of the answer is. Let's see what the book got. They got y is equal to e to the minus x over 2. Got it. They wrote the minus cosine 2x in front. Oh, whoa, whoa, whoa. I messed something up here. And I don't see how I did it. When I took the derivative here, that gave me plus 2 C2 cosine 2x. Got that. x equals 0, seems like to me. Oh, no, I think I did that right. 2 times C2 times cosine of 0 is 1. Now they got a plus 1/2 there, which I'm not seeing. Something I've missed here. Oh, of course. Of course, sorry about that. I only did half of the product rule. Sorry about that. Okay, scratch some stuff here. Sorry about that. I got carried away. I knew it was coming out way too easily. That's just half of the product rule. Sorry, folks. Okay. Let's do the other half of the product rule. Okay. We did y prime the first times the derivative of the second. We still got to do plus the second, which is, I'm going to write it this way, C2 sine 2x minus cosine 2x times the derivative of e to the minus 2x, which would be, and I'm going to move that plus sign because it's not going to stay a plus sign. When you take the derivative of e to the minus 2x, you get a minus 1/2 e to the minus 2x. X over 2, but is what I was trying to write. I hate this thing. That's an x there, and that's a 2 down there. Okay, that's what we've got. Okay, so let me clean that up a little bit. If I can get the pen to show back up somewhere. Here's my y prime is equal to e to the minus x over 2. I can probably just leave that off because that's always, well, I don't want to. Okay, 2 times the sine of 2x plus 2c2 times the cosine of 2x. That's not right either. That's a minus there. No, it is. That's right. That's right. Yeah, that's right. That last x looks terrible. Okay. Okay. Minus 1/2 e to the minus x over 2. I'm not going to have room for the parenthetical part here, so I'm going to write it down here. Actually, what I'm going to do, I'm going to make that a plus here and flip these back again and make that a cosine of 2x minus c2 times the sine of 2x. I can't get that I to right. Okay, now I plug in 2 for the y prime. Jumped the gun on it big time last time. I can't get my curve. There it is. So that's going to be a 2 is equal to, and e to the 0 is still 1. Okay, and cosine and sine of 0 is still 0. So here we have a 2 C2. That part we had before, but we also have a plus 1/2 from here, and e to the 0 is still 1. And then this is time cosine of 2x of 0 is 1, and then that gives you a minus 0. Alright, let's see what we get here. It's not looking good. I think I made another dumb mistake, but let's see what we got. Let's subtract 1/2 from both sides, and you get 3/2. 4/2 minus 1/2 is 3/2 is equal to 2C2, and then divide by 2 and you get C2 is equal to 3/4. So it does work out. Okay, now the only problem is we have absolutely no place to write our answer, so I'm going to have to go in and write and do some erasing here. There we have it. There we go. All right, so let's erase all this. We don't need it anymore. I hope we don't need it anymore because I am erasing it all. I think that will give us enough room to write our answer. So let's come back and write our answer. So what's our general solution then? Y is equal to e to the minus x over 2, that doesn't change, okay, times the C1 was a minus 1, the C2 was a 3/4, so I'm still going to write that first. That's going to be 3/4 sine of 2x minus cosine of 2x. Okay, that's my final solution now. Let's see if we got it right this time. Y is equal to e to the minus x over 2, got it, times, and they put the minus cosine 2x in front, which is okay, plus 3/4 sine e to the 2x, got it. Okay. Now, let's set this aside for just a moment here and go back to the board, okay, to the book, sorry. Okay, here we go. There was a solution no, that was the previous one. Here's the one we were just working on, and there was a solution. Y is equal to e to the minus x over 2 times, they put the minus cosine 2x in front, plus 3/4 sine 2x behind. That's fine. Now, they then say 2 equations worth knowing. I'm going to scroll on. Oh, wait. Sorry. Here happens to be the graph, which I sure didn't want to do, of the solution that we got there for that initial value problem. It's going to be the e to the minus x over 2 is, I don't know if you remember before, that's called the transient term, meaning as x is very large positively, the e to the minus x over 2 is going to make that get very, very, very small. So this is approaching 0. For large values of x, this gets closer and closer to 0. It bounces around above and below and above and below, but gets closer and closer and closer and closer. Okay. Now the other part, the cosine and sine, the sum of those two, basically is going to give you a sinusoidal curve of some nature, but it has to fit inside the envelope. If you remember what did they call these before? Goodness gracious, they had a name for them. I call them envelope. That's not what you call them. The e to the minus 2x explodes for very large values of e, and that's what you see happening here. You could take and superimpose on top of this a thing coming down here, and that would be the exact graph of e to the minus 2x. Okay, x over 2, minus x over 2. And if you found this point where it finally was here and came up here, that would be minus e to the minus x over 2. And that forms the envelope that your sinusoidal curve goes inside. So I call this a variable amplitude problem, because your amplitude, back with sines and cosines, remember the number that went in front was your amplitude. Well, here you have a variable out in front, e to the minus x over 2. So that's why that became what your amplitude was, as these are coming down, forming your solution. Now, there's a whole bunch of them you can fit under that, but when x equals 0, y is negative 1, which sure enough is what you have there, and the slope of there is going to be 2. Now that's hard to tell on this graph, but that is a slope at that point of right around 2. Now the reason it doesn't quite look like it is that the scales are off just a little, I think, but maybe not. Maybe that does a 2 there, because it looks like to me these may be a little bit longer this way than you are that way, but maybe not. Maybe they are the same, but that's the slope of 2. So certainly this fits the bill. Okay, so let's scroll on down then and get to these two equations worth knowing. Okay, the first of these is y double prime plus k squared y is equal to 0, where k is any real number. You don't want it being a complex number, but any real number, well, any complex number with an imaginary component. These are important in applied mathematics, and that first one, the auxiliary equation, is m squared plus k squared is equal to 0, which is m is equal to plus or minus ki. Okay, so there you have your sine and cosine. That is exactly the function you get from that. It's always going to be a c1 cosine kx plus c2 sine kx. The k's show up again down here, here, and here. Not k squared, but k, square root of that coefficient there, shows up down here. Those are your sinusoidal curves, and you sort of know that because the second derivative of a cosine is a minus cosine. Second derivative of a sine is a minus sine. Okay, but you got some k's thrown in there, so that's where those come from. But that's why when you add that to the second derivative plus that will have to equal 0. If on the other hand it's a minus k squared, then that's a much easier one to do. That gives you a plus and minus k as here is your auxiliary solution. M squared minus k squared is equal to 0, so that's m plus k times m minus k, so m1 would be plus k and m2 would be minus k, and that gives you e to the kx plus c2 e to the minus kx. Okay, those are your good old exponential functions, because well, they all come from exponentials, but this one, because the second derivative of an exponential function is going to be just like the first derivative, but it's just like the function, except so you put a minus sign in front and you take care of that. Okay, now this happens to be the plus in there, the hyperbolic cosine, which I don't care for hyperbolic functions, but if you're in a major that uses them a lot, know that. Okay, 1/2 of this thing is your hyperbolic cosine, and 1/2 of the difference of those two would have been your hyperbolic sine. And since the hyperbolic cosine and hyperbolic sine are linearly independent of each other, you can also write this as that type of a form. It's not immediately obvious how that comes to play, but if you added this equation to that equation, you will get, you'll see that the minuses go out here, and you wind up with pretty much this is a solution. But I don't like messing with it. I'm just perfectly happy to leave it in this form here than to write it in this form here. This to me is far easier to work with than that. So I don't usually go back and change those, but they are indeed true if you want to do them. So let's go to higher order equations. Okay. Now again, remember we're going to have constant coefficients, so your a sub n minus 1, a sub n minus 2, all the way down to a sub 3, a sub 2, a sub 1, a sub 0, all constants, no functions of x. They could be any kind of constant, positive, negative, fraction, decimal, rational, irrational. They could even be 0, except for your a n. It can't be 0, but it could be anything else. Okay? So your assumed solution is y is equal to e to the mx. Okay? Then if you would do the first derivative, second derivative, third derivative, all the derivatives for it, you come up with a well, now they're doing something rather strange here. They're giving you the total solution. They're not telling you how to get there, but they're giving you total solution. Y is equal to C1e to the m1x plus C2e to the m2x plus C3e to the m3x for every different solution. And this is what they're saying here. If all those roots, if you did your function, ACE, they've really messed up your thing here. That would be if your a sub n, okay, I'm sorry. Here they have it, what I was going to say. This is your auxiliary solution then. Auxiliary equation then. It's a polynomial, okay? A sub n m to the nth power plus a sub m minus 1 m to the m minus 1 power all the way down to a sub 3 m cubed plus a sub 2 m squared plus a sub 1 m plus a sub 0 equals 0. Now, in general, that's not a particularly easy thing to solve. However, if you remember back from pre-calculus, it's doable most of the time, okay? And here's how you do it. Remember we had the rational zeros test? You do all the possible factors for a0 over a sub n. Remember a sub n can't be 0, so you can do that. All the possible factors there, and then start doing synthetic division to get it down and find your solutions, m1, m2, m3, all the way down until you get those last two. And when you get those last two, they can be, that forms a quadratic. That quadratic may have real or imaginary parts to it, just like we did earlier. So you get down to that. Now, it's harder to, if all these are real and distinct solutions, yeah, you just write them down. Y is equal to C1e to the m1x plus C2e to the m2x plus C, all the way up to C sub n e to the m sub n x, if they're all real and distinct. But if you do have multiple solutions, that's case 2. Remember, it's not limited to 2 now. It could be 4, 7, however many repeated solutions. Then what you have to do for that case is for every one you have, say, if you have 4 repeated roots up here that m sub 1 and m sub 2 and m sub 3 and m sub 4 are all the same, then you have a c1 e to the m1x plus x c1 or c2 x e to the m. If you have 4 solutions, then you have 4 powers of x. Well, zero power, first power, second power, and third power. So you'd have up to x to the k minus 1. So that's how you handle it if your case 2. If your case 2 was multiple roots, okay, and you could have more than one multiple root too, but let's just take one at a time, then you'll have a power of x. You'll have e to the m1x, the first solution, then an x times that, x squared times that, x cubed times that, up till x to the k minus 1 times that. Okay? So then your general solution would be some linear combination of those, c1 e to the m1x plus c2 x e to the m1x, still the same m there, plus c3x squared e to the mx plus c3, all the way up to that one. And that will handle any multiple roots you have. Okay? Now, here's what they say, a little statement here. It should be remembered that when the coefficients are real, complex roots of an auxiliary equation will always appear in conjugate pairs. Thus, for example, a cubic polynomial can have at most 2 complex roots, 1 real root and 2 complex roots. A quartic, 4th degree polynomial could have 4 real roots. Now we're not going to count any repeated roots. Or it could have 2 reals and a conjugate pair of complex, or 2 conjugate pairs of complex numbers. But anyway, they always will come out in, if you have any imaginary parts to them, they're always going to come out in conjugate pairs. And then you can do your, for each conjugate pair, you can do your e to the alpha x plus b to the plus times c1 cosine beta x plus c2 sine beta x. All right, so let's do a third order differential equation. There it is. So let me go to the whiteboard. How are we doing on time? Okay, we only got about 9 minutes. Let's see if we can get this one done. If I can get my cursor to show up somewhere here. There it is. Okay, so let's go to the whiteboard. And let me get my pen. I'm going to do this. Easier to do it with my finger here, but easier to write with the stylus. Okay, so here's, where are we now? We did example 2, we're doing example 3. Okay. We have y triple prime. Why this will not write, I don't know. I haven't figured that out yet. Y triple prime plus 3y prime, double prime, notice we're missing a y prime here. Minus 4y, that's equal to 0. Okay. That's all I need. It's not an initial value problem, so we're going to have arbitrary coefficients. Okay, so what's our initial thing? Assumption, let y equal e to the mx. So write down your auxiliary equation. M cubed plus 3m squared minus 4 equals 0. Notice we do not have a first derivative in that, so we do not have a linear term in our auxiliary equation. All right. Now, the technique here, if y'all remember, rational coefficients. We look at the ratio of all the possible factors of the constant term over the leading coefficient. Leading coefficient, of course, is 1, so that's going to be pretty easy. The factors there, your P over Q is what you call it, rational things, are not even going to be necessary. I mean, they are rational, but they are plus and minus 1, plus or minus 2, and plus or minus 4. Those are your only possible factors of P over Q. So Q's got to be 1, basically. The easiest one to do is that plus 1. So let's start with that one. If that would be plus 1, if that would be your solution, then, and this would be M. Let me write this down. I didn't write that. That would be your M. Otherwise it would have been X, but yeah, we're doing that. That's the solution. If that is plus 1, then all you do is look at your coefficients. 1 plus 3 minus 4. Sure enough, that is equal to 0. So M equal 1 is a solution. So let's write it down. M equal 1. That is your solution. So let's call that M1. Okay? Okay. Now, that you know as a solution. Now, what we do to find the next one is synthetic division. Since you know that M is 1, okay, then you do 1 on the outside and then do your coefficients on the inside. 1, 3, remember you have to account for that missing term, 0 minus 4. Okay, if you remember synthetic division, skip a line, draw a line. That's my rule. Bring down the 1 and then you multiply and add. 1 times 1 is 1. Add, you get a 4. 1 times 4 is 4. Add, you get a 4. 1 times 4 is 4. Add, you get a 0. You better get a 0. If that was a solution, which we knew it was, it better have a remainder of 0. Once you get 3 numbers down here, you stop. And by the way, back up here, when you're doing the synthetic division, you better have 1 more than your maximum exponent. Maximum exponent was 3. You have 4 numbers there. You've got enough. If you had just written down 3 numbers, you knew you wouldn't have enough because you have to have 1 more number here than you have maximum exponent there. Okay, so what does this mean? Your final is going to be M squared plus 4M plus 4 is equal to 0. Now I hope you look at that and realize that's a perfect square trinomial. That would be M plus 2 squared. But if you didn't see that, it's okay. And what that tells you is M is equal to minus 2 is your one and only solution. It's a double solution. So that would be your M2. Okay? But it's a double root, so we know what to do with that. So now we can just write down our solution. Y is equal to C1 e to the x, that's with M1 equal 1, plus C2 e to the minus 2x plus C3. We don't have one, but this is a double. So remember what we do with a double root? Put an extra x in front, e to the minus 2x, and then use that same thing. There's your solution. That's it. Well, let me say it's it. Let's see how the book did. Y is equal to C1 e to the x plus C2 e to the minus 2x plus C3x e to the minus 2x. Got it. That's exactly what they get as a solution. Okay. And it's almost just a write down. Not quite. You have to do a little bit of work. You have to remember your rational zeros test. And with that, you might want to go back and remember Descartes' rule of signs and other things like that. When you need them, use them, okay? But this was pretty simple to do. We just took the first one of those possible roots plus 1, plugged it in, and we found that we had a root there. Once you did synthetic division, you had it down to a quadratic. When you get to a quadratic, stop, factor, quadratic formula, whatever it takes when you get to that quadratic step. Here we could factor it, so it's a double root, so there's our solution. All right, it looks like we're going to have to stop there this time because we've got 1 minute left. So let's mark this to start at example 4 next time. Let me also erase where my mark was last term, which was over at example 5. Erase that. And let's see if we can come up with some homework exercises for you. Oh, we almost, amazingly, got very close to finishing 4.3. Okay? Homework exercises here would be any of the odds 1 through 13 that are in the back of the book. Please do those. Then do any of the odds 15 through 23. Now, 27. I say those. Some of those we may not have done an example like. So if you get stumped, hold off. We're going to do two more examples. We're going to do example 4 and 5. And by the time we finish those, you should be able to do all those. So do as many as you can of 15 through 27. But if you do get hung up, stop, and we'll get the rest of those covered next time. Well, actually, I know you can do 29. That's an initial value problem. Probably 31 as well. That's an initial value problem. 33. You can try 35 if you'd like. Hang up if you get stuck. And then there's a couple boundary value problems. We'll wait and do those next time. Okay. Any questions? All right. Good deal. We ran right out of time. So if there are no questions, I will start shutting us down. Speak now or forever hold your peace. All right. We'll see you on Thursday. Okay? If there are no questions, I'm going to end the meeting. There it goes. All right.